Name is Aditya Rajarajit and my registration number is URK23CS1010. So today we'll be doing experiment 3, which is regression techniques. And in this experiment we're building three different types of regression models from scratch on a wide data set. So we'll do simple linear regression, multiple linear regression and logistic regression, all without use of the scikit-learn for the model building. So uh, so so here's the plan. First, we'll predict the wine quality using this alcohol content, and that's simple linear regression. Then we'll add sulfates as another predictor. Then that is multiple linear regression. Finally, we'll classify wine type using all chemical features. And that's logistic regression. We'll calculate all the metrics manually. Uh, like sum of squared error, root mean square error, r squared, accuracy, precision, recall, everything from scratch. So so let's go to part one, simple linear regression. Question 1.1 is just loading the data, and question 1.2 is data uh, is where data cleaning is done. I check for missing values and impute them with the column mean. This is important because null values will break our calculations later. So now for question 1.3, choosing our variables. For even register numbers, we use alcohol as our independent variable x and quality as our dependent variable y. I extract these as number arrays. Then in question 1.4, it's where the math happens. We calculate B0 and B1 using the formulas. So B1 is the slope and is the sum of it's x minus x bar times y minus y bar divided by the sum of x minus x bar squared. And b0 is the intercept, it's y bar minus b1 times x bar. And I display all the intermediate values so you can see how it works. Then for question 1.5, we formulate our equation predicted equals b naught plus b1 times x. Then I calculate predictions for all our data points and show the first 10 compared to actual values. Then in question 1.6, this question calculates the sum of squared errors. So this is simply the sum of actual minus predicted squared. It measures how wrong our model is. Then in question 1.7, this gives us the root mean square error. So I calculate the mean square error first by dividing the sum of square error by number of samples, then take the square root. So the root mean square error is in the same units as our target, so it's more interpretable. Then in question 1.8 is the R squared, the coefficient of determination. This uh, this tells us what percentage of variances in quality is explained by alcohol. So I calculate total sum of squares first. Then R squared is 1 minus sum of squared error divided by this one, SST. So a value close to 1 means our model fits well. So we plot the regression line with actual data points. You can see the line going through the cloud of points. Then finally, in question 1.10, I take user input for any alcohol value and predict the quality. I also show this prediction on the plot with a marker. So moving to part 2, multiple linear regression. This time we have two independent variables, alcohol and sulfates. So from questions 2.1 to 2.3, basically what we do is they're kind of similar. We load data and choose our variables. X1 is alcohol, X2 is sulfates, Y is quality. Uh, Question 2.4, instead of simple formulas, we use matrix operations. So I create a design matrix with a column of ones for the intercept, then alcohol, then sulfates. The normal equation is beta equals inverse times x transpose y. So I show each step calculating xtx, its inverse xty, and finally our coefficients b0, b1, and b2. This is linear algebra in action. Then in question 2.5, this gives us our equation y predicted equals b0 plus b1 times alcohol plus b2 times sulfates, and I calculate predictions and show the comparison in question 2.6. 2.6 to 2.8, really basically what happens is calculations of sum of square error, root mean square error, and r square, just like before, but now for our multiple regression models. So the r square is usually higher than simple linear regression. Adding more relevant features improves our model. So yeah. Then for question 2.9, I take both alcohol and sulfates as input and predict quality. The 3D visualization is, as you can see, is right here, and you can see the regression plane instead of a line. So points above the plane are under predicted, below are over predicted. Moving on to part three. Part three is logistic regression. And this is a classification, not regression despite the name. So we are predicting the wine type now. So from for questions 3.1 to 3.2, basically what is happening is we load the data and pre-process it. For logistic regression, we need to encode our target. So I manually create a mapping. So iris setosa becomes 0, iris versicolor becomes 1. So I handle missing values with the mean imputation. So for question 3.3, I chose variables. Here X is all chemical features, Y is encoded Y type. Now for question 3.4 is the heart of logistic regression, gradient descent. Uh, Let me explain what's happening here. First, I split the data into 80% training and 20% testing manually using random permutation. Then I standardize the features. So I define the sigmoid function. So sigmoid function basically it passes any value to between 0 and 1, giving us probabilities. So then I initialize weights to zeros and set a learning rate of 0.01. So the gradient descent loop runs for 1000 iterations, and in each iteration, what I do is I calculate z, then I apply sigma to get predictions. Then I calculate the gradient. Then I update weights and bias by subtracting learning rate times gradient. And then I record the cost using binary cross entropy loss. I print progress every 100 iterations so you can see the cost decreasing. Then in question 3.5 plots this cost against the iterations. So you should see a smooth, curve, smooth downward curve. That if you see a smooth downward curve, that means our model is learning. So in question 3.6, basically what happens is it evaluates performance. So I calculate the accuracy. I build a confusion matrix manually and compute precision, recall, and F1 score for each class. I also create visualizations and the confusion matrix, heat map, probability distribution, and so on. So uh, look at our test accuracy. If it's above 90%, our model is doing great. The confusion matrix shows exactly which samples were misclassified. So, yeah, that's basically the end of this experiment. Thank you.